All right, kids. So today we're looking at the law of cosines. This is the formula for it, and it's not a joke. It really is kind of a nasty formula. All right, but the good news is that they typically they will tell you to use the formula whenever when you're asked to use this sort of thing. Okay. Uh, so your responsibility is really just going to be learning to apply the formula. In this video, I want to mention real quick the best cases or when you might use the formula, when to look out for it. And also, we're going to talk about a proof in proving this. All right. Will probably be a two-part video actually because of the proof is kind of long. All right. So, one of the best places to use this formula is when you have three sides of a triangle. Let's say you know A, B, and C, but you're trying to solve for one of these missing angles. That would be a good time to use it. Because if you actually know what lowercase a, b, and c are, right? A, B, C, A, and B, well, you can use that to solve for angle C right here. All right, you just have to algebraically manipulate it a little bit and use your inverse cosine, and you'd be able to solve for a missing angle. Another good place to use it is when you have two sides and you know the included angle. All right, here I have 8 and 6, and uh, I know the angle that's in between them. We could use we could use this information right here to solve for this missing side. Let's just call it side C. So side C would be the one that we're actually solving for over here, and I know this right here would be like a 50 degrees, okay? And then this could be A and B. Anyway, let's we'll get into actual examples later of implementing it, and it's not too bad really, especially when you're using your calculator. All right, what we want to start with as far as the proof on this is we want to start with the coordinate plane. All right, this is one proof for the law of cosines. And I'm just going to keep this in quadrant one. You could adjust this proof so that it accounts for obtuse triangles, ones that might slip into quadrant two or quadrant four. But let's just kind of wave our hands there and ignore that, shall we? All right, we're going to consider the most generic triangle on Earth. All right, uh, triangle, this is going to be point C. Over here is going to be point B. And then up here is going to be point A. All right, so this is a super generic triangle. We don't know much about it. We don't really care if it's a right triangle. We're going to be applying this to this formula applies to right triangles, but it also applies to non-right triangles as well. All right. So imagine any triangle out there. You can take that triangle and reorient it. All right. You can reorient the triangle so that whatever like the base is, one of the side lengths, so that you could lay it in such a way that the vertex would lie at the origin. That's what we're doing. We're forcing vertex C, one of the vertices, to be at the origin. And then whatever the other vertex is, it's going to lie on the x-axis, all right? Now, if I label the sides here, this length would be side C, all right? It's the side that's across from angle C. And then this being angle B would force this one to be side B. And across from angle A, this is going to be side A. All right, so far so good, I'm sure. Coordinates. All right, the coordinates for point C, let's point up to it. That's easy. That's 0, 0. The coordinates for point B, all right, for point B, Well, I know the y coordinate. I know the y coordinate's 0 because it's 0 up and down. The x coordinate is going to be how far along it is this way. Well, that just so happens to match the side length A. Right? I don't know the coordinates for point A. That's going to come later. We're going to figure out the coordinates for point A. And let's see. Let's just, I think we'll pause right there.